Greetings, physicists. This video will be talking about how to calculate the energy of a simple harmonic oscillator. And we will start with a spring. We're going to assume that this spring is on a frictionless horizontal surface, and it's going to be, if this is the equilibrium position, we'll stretch it to some amplitude A. So there's an amplitude of A, and then we will release it, and we know it's going to oscillate back and forth between its position here, its equilibrium, and equal distance compression, and back and forth. We covered that before. But now we're interested in the energy. So let's consider first this situation. When the spring is unstretched, when it's at equilibrium, we can say that it has no spring potential energy. Spring potential energy is 1/2 kx squared, but at equilibrium x is 0. If it's not moving, then it has no kinetic energy, and if it's lying on the ground, it has no gravitational potential. So what we're really going to be interested in is this point, where it starts with some stretch. So at the beginning of the stretch, before we release it, it shouldn't have any speed and it shouldn't have any height. So there's mgh equal to 0, and there's half mv squared equal to 0. So the only kind of mechanical energy available to it is spring potential, and that would be the spring potential energy equal to 1/2 kx squared. But in this case, the distance it's stretched is the max amplitude A, so we can just kind of rewrite that as 1/2 ka squared. And once we release it, as long as this is an isolated system and there's no friction or anything, it won't lose any energy. And so that energy, this is the total mechanical energy that it will have. In other words, whatever we start it with, it has to maintain that energy, it has to conserve that energy. So that's the initial starting condition. 1/2 ka squared will be its total mechanical. Now, we're also going to look at a point, so that's the initial condition. Now let's consider, let's consider a point in here somewhere, where this is equilibrium, this is max amplitude, and then this is some point x in between. So this is like 0x, this is 0 displacement, this is x amount of displacement, this is a amount of displacement. So at this point x, it will not have lost all of its spring energy. The spring will still be stretched from equilibrium by some amount less than a. So it has some of that, but now it is moving. It'll have some velocity at that point as well. So we have to consider that. So when we come down here, the energy it started with will now be turned into a little bit of 1/2 kx squared, noting that this is less than the 1/2 ka squared because x should be always less than a, except when it is equal to a. And then plus, it should have some 1/2 mv squared. It won't have gained any height, so we don't have to worry about gravitational potential. And this is generally the equation for simple harmonic motion. You start the object with some amplitude, which gives it some amount of this potential energy, and then it will end up with, at any point, some of this and some of this. Now, if you were looking for what's the maximum velocity it can get to, it's going to be at the point where it's lost all of this kind of energy. So you could say that when this is 0, the initial spring potential energy, which was the total mechanical, will be equal to 0 here plus 1/2 mv squared, and that's where we're going to get maximum velocity. So that energy equation is another way to show what we had looked at before, which is that once it passes through the equilibrium position, it is going as fast as it possibly can. Okay. And if we solve that for, like, let's say we want an equation for that maximum velocity, well, the 1/2 is going to cancel. And if I divide by m and square root, I should get that Vmax is equal to a, because the a squared gets square rooted, times the square root of k over m. All right, so there's a Vmax equation for you. Now, we had a Vmax equation before in the other lecture about simple harmonic motion. We had this. We had that Vmax could also be calculated with this formula, 2 pi frequency amplitude. Remember that one? Well, let's set these things equal to each other. 2 pi frequency amplitude equal to A, amplitude, square root of k over m. Well, amplitude cancels. And we could solve for frequency and get frequency equal to 1 over 2 pi times the square root of k over m. And we could even get an expression for period. We could make period is just 1 over f, right? So if we just invert this, 1 over 2 pi is 2 pi, 1 over k over m is m over k. So square root of m over k. And so these are equations that will be useful to us. Notice that the time it takes the spring to oscillate back and forth does not depend on the amplitude. That canceled out. So if you have a spring with a period of 2 seconds, for instance, whether you stretch it to 10 centimeters or whether you stretch it to 10 meters, assuming that it stays linear for that stretch, it will still have a 2-second period. That's an interesting finding. All right. So those are our equations for the spring. We're now going to talk about the other big simple harmonic oscillator, which is a pendulum. So let's have a pendulum here. All right. Well, we had this for a pendulum. So let's say that we have a pendulum and it's got an angle theta with the vertical. And I'm just going to draw a free body diagram, but I'll kind of draw it on the object itself. It's got a tension this way that's in the string, and it's got an mg going down. But it doesn't actually move down. It moves sort of tangent to that radius, right? We know it's going to sweep out this kind of circular arc. And so its velocity at that point is 90 degrees to that tension. So I'm going to resolve the mg so that the components of gravity are both perpendicular and parallel to its movement. So there will be a perpendicular arrow this way, and then this kind of arrow here will be a component of mg as well. And this theta here is going to be, make sure I've got this right. If I rotate this theta degrees this way, then that theta would be here. So this is a cosine. This is an mg cosine theta, and the perpendicular one is mg sine theta. And notice that the tension should cancel out with the mg cosine theta because the object is not moving in either of those directions. It only moves parallel. So if we're doing a net force, the net force is this one. The F net equals mg sine theta. We're going to do an assumption here, ladies and germs. And that assumption is this. That sine theta is very close to, I'll put a little approximation there, approximately the same as theta if, and this is big, you have to be doing this, if you're in radians and, there are two assumptions, if you're in radians and theta is less than 10 degrees or so. Even if you go up to like 10 degrees, if you change that to radians and take the sine of it, you get something like, you're only like 10% off of the actual theta. So for very small angles of theta, we can make an assumption, which is that sine theta equals theta in radians. And so what that means is when I start doing the rest of my conversions and stuff here, the rest of my algebra, I'm going to be using angular coordinates, angular stuff, because that's all in radians. So we have F net equal to mg sine theta, and in radians at less than 10 degrees, we're also going to say that that's pretty much the same as mg theta. That's not perfectly true. So when you guys are doing experiments and you want this math to work out, don't pull your pendulum past about 10 degrees. Or these relationships, the error essentially becomes too big. Okay, so we have that. Now, remember, if we're talking, so this is FNet. When we're talking about this thing, it's going along this circular path. So that path has a linear distance x, which is the same as an angular distance theta, and x is equal to r theta. That comes from our rotational motion unit that we just finished. So I'm going to take that and divide by r and get theta equal to x over r. And in this case, the radius here, is actually the length of that pendulum. No matter where it is, that string is length L long. So we're just going to say, we're going to use, instead of radius, I'm just going to replace that with L. So theta equals x, x being this distance here as we go around the arc, divided by L. So let's take that theta and put it back here. So we have the net force equal to mg times the arc length x divided by the length of the pendulum. Good. Okay, now we're going to go back and remember some of our other equations we had for a sinusoidal function, which this will be. This will be a simple harmonic motion function. So that x, that path that it travels, and it's a curved path, but it's the position of this pendulum over time, can be calculated with this formula, a cosine of 2 pi f t. Now, we can also say, though, that instead of, like, we have this, we have theta and we have x, we could also say that theta follows the same thing. Theta and x are directly proportional to each other. So we could make a similar equation saying that theta would be equal to some theta max, I guess, because a is really x max. So we could say that the maximum theta, or so if you pull the pendulum to 10 degrees, 10 degrees is the maximum that pendulum will ever get to, right? Law of conservation of energy says it can't swing higher than 10 degrees. If you pull the 9 is the theta max. Of course, you would do this in radians. So, did you get the idea? So this, whatever theta it's at any given time is equal to the maximum theta you pulled it back to, which is again like an amplitude, times the cosine of 2 pi ft, and that still works. So either of these equations are useful. Now I'm going to make a parallel here to what we did earlier with the spring. With the spring, so this is all about force, right? Well, with a spring, a force is like this: F equals kx. Well, look what we have. We have F for the pendulum equal to mgx over L. So the parallel here is those are both types of simple harmonic motion. So they should have similar equations. So what I'm going to do is, anytime I see a k in the spring equations, I can make a similar equation for the pendulum, but I'm just going to use mg over L instead of k, because the pendulum is basically getting a force related to its position based on this mg over L factor. Make sense? Hopefully. So in the spring, we had this. We had 2 pi times the frequency equal to square root of k over m. Remember, amplitude canceled. So in the pendulum, we should have this. We should have 2 pi times the frequency equal to the square root of, well, I'm going to use this instead of k, so mg over L. And then there's an m on the bottom that I have to keep in there. Well, the m's will cancel. That's good. So the frequency of a pendulum, if I just solve this for frequency, so for a pendulum, the frequency equation becomes 1 over 2 pi square root of g over L. And I can do my period equation is just the inverse of that, which is 2 pi square root of L over G. That's nice and tidy. Okay, so we have period and frequency equations for pendulums and springs, and for both of them you can use half, well, for the spring we had half Ka squared was the energy, equal to half at any point after you let it go, equal to half Kx squared plus half mv squared. With a pendulum, it's a little bit, I think, easier. The pendulum doesn't have an elastic constant, right? It just had that mg business. But you can probably visualize this better if you just do it with height, right? And then so we have like 3 different points in the pendulum. So whatever you release it from, that's maximum height, which is kind of like its amplitude. Okay, and so it has, and it doesn't have any speed yet. And it's not stretching, so it doesn't have any elastic. So it really starts with mgh for the pendulum. That's its total mechanical energy. H max, you could say. And then at any, so we'll say H max. And so at any point after that, it will have some mgh, plus it will, and then that H will be less than H max, and whatever it lost of mgh, it gained as 1/2 mv squared. So that's not really that new to us. We saw that in the original energy chapter. Okay, that's going to be it for energy of simple harmonic oscillators.